This is a satellite foundational course for GOES-R on fog formation and dissipation, with a focus on how to detect fog. I'm Scott Lindstrom from SIMS, and I will lead you through this training. Learning objectives are on the left. You'll learn which GOES-R ABI channels and products can be used to detect fog's presence and to monitor its evolution. Note the acronyms you'll see in this training, boxed in yellow at the bottom. Subject matter experts for this training are listed on the right. Mike Pavlonis from NOAA and Corey Calvert from the Cooperative Institute for Meteorological Satellite Studies were both integral in the development of GOES-R's fog detection products. Here's one of my favorite figures. Brightness temperature detection of stratus clouds made up of water droplets works because water droplets in clouds are not black body emitters of 3.9 micrometer radiation. The conversion of satellite-detected radiance to temperature assumes that an emitter is a black body. For the case of 3.9 micrometer radiation above cloud droplets, then, where the amount of radiation detected will be less than that emitted by a black body, the inferred temperature is cold. Clouds do emit 11 micrometer radiation more as black bodies, so the inferred brightness temperature won't be so cold. In this cross-section from a fog bank to a cirrus deck, you see brightness temperature differences over the fog that are related to emissivity differences in the cloud, so that the 3.9 micrometer brightness temperature is cooler than at 10.7 micrometers. Over the cirrus, subpixel effects cause a difference so that the 3.9 micrometer brightness temperatures are warmer than the 10.7 micrometer brightness temperatures. In clear regions at night, the 10.7 and 3.9 temperatures are similar. You can learn more about subpixel effects in the GOES-R Cloud Products module. In this AWIPS image, the night fog brightness temperature difference is loaded over its constituents, the 3.9 and 10.3 micrometer imagery. Note the probe over the Bay Area. Brightness temperature at 3.9 is 3.75 Celsius, is colder than it is at 10.3 micrometers at 8.57 Celsius. This is because of emissivity differences in stratus clouds. For the probe in the northwest part of the image, the brightness temperature at 3.9 micrometers, minus 16.5 Celsius, is far warmer than at 10.3, about minus 30 Celsius. That's because of, in part, subpixel effects. The 10.3 micrometer detectors are more sensitive to the colder part of the pixel, and the 3.9 micrometer detectors are more sensitive to the warmer part of the pixel. The green part of the night microphysics RGB is the night fog brightness temperature difference that you just saw, as you can tell by this toggle. In the absence of high clouds, this RGB can give information on stratus decks. Whether or not stratus is a fog bank has to be determined in other ways. Observations at airports, for example, or webcams, something like that. Stratus is indicated in these images by the brightness temperature difference field is enhanced in blue, meaning positive values at night. It's hard to see that difference in the 3.9 and 10.3 micrometer images individually. That difficulty in seeing the difference doesn't happen all the time, however. The nighttime microphysics RGB imagery also indicates stratus, with a blue cyanish hue in the same region as the brightness temperature difference field. Note the color in this September imagery is different from what we just saw over the Bay Area in March. This one. Where there are multiple cloud layers, such as northern Georgia, it's hard to tell if there's surface fog. That is there stratus under the high clouds that are over Georgia and Tennessee? How can you tell? If you wanted to create an algorithm to detect fog, instead of the nebulous term fog that can mean all sorts of things, you might rely on IFR conditions. That's what's been done for GOES-R. IFR probability combines satellite detection of low clouds and stratus with rapid refresh model information, answering the question, is there low-level saturation? If both of these things are true, IFR probability is large. If the satellite cannot view low clouds because cirrus is in the way, for example, IFR probability can still be correctly large because the model says low-level saturation is present. If the satellite-detected stratus deck is elevated off the surface, IFR probability can still be correctly smaller because the rapid refresh will not show low-level saturation. IFR probability fields have the same resolution as the IR sensors. 2 kilometers is the subsatellite point. Consider the scale of fog as you look for signals. Is it smaller scale than the model? Is it smaller scale than the satellite? Here's that view over the Carolinas. But IFR probability has replaced night microphysics RGB. IFR probability is large over northern Georgia, correctly, because the rapid refresh there is showing low-level saturation. There are actually 3 probability fields for MVFR probability, IFR, and low IFR conditions as shown here over New England. As you might expect, MVFR probabilities are always greater than IFR probabilities, which are always greater than low IFR probabilities. Cloud thickness in the bottom right is a GOES-R product that estimates the vertical thickness, cloud base to cloud top, of the lowest water-based cloud layer. This product is essentially a lookup table that compares 3.9 micrometer emissivity to SODAR observations of cloud thickness off the west coast of the US. GOES-R cloud thickness is not created in regions of multiple cloud layers because satellite information on the lowest layer is missing in such cases. GOES-R cloud thickness is also not computed during twilight conditions because of rapid changes in the reflected component of the 3.9 micrometer radiation. The fields shown here have 2 distinct regions. Over coastal Maine, the satellite has an unobstructed view of low clouds. Probability fields are pixelated, reflecting the variability inherent in satellite data. GOES-R cloud thickness can be computed there because the satellite sees the lowest clouds. High clouds are present over eastern Massachusetts and northern New Hampshire, and probability fields there rely on model data, and they consequently look much smoother because of smoothing that occurs in the model and because of the relatively coarse model resolution. Cloud thickness is not computed in those regions. In the animation at right, persistent cirrus over Washington and Oregon prevents the satellite view of low clouds. You might know as a season forecaster where low clouds are most likely. There are occasional holes in the high clouds that allow the signal of lower clouds to peek through. But where would you expect the lowest ceilings and poorest visibility? Note that strong low cloud signal over southwest Oregon. Is that fog or low stratus? What might you look at to decide? Here's the GOES-R IFR probability for the same time. So it's using model data in regions where the cirrus cloud prevents the satellite from seeing the lowest clouds. But the model's saying there's saturation offshore and in the high terrain over western Washington and western Oregon, except around Portland. This example demonstrates the utility of cloud thickness in predicting dissipation time. The still figure is cloud thickness, the last one before morning twilight conditions, and in fact you can see the data cut off right off Florida's east coast. Values are very small. Magenta is around 300 feet, blue is closer to 400 feet. Those small values suggest rapid burn-off, and that's what's happened, as shown in the inset animation. The region with the thickest fog diagnosed had fog for the longest time, but that is almost gone by 1307 UTC, 2 hours after the cloud thickness image. GOES-R cloud thickness, the last one before sunrise, that's on the y-axis, and fog dissipation time, on the x-axis, are related. The points on this graph were determined by hand for radiation fog only, mostly for cases over the southeast US. If the last cloud thickness value before sunrise was at 1145 UTC, and it showed a cloud thickness of 900 feet, the best fit blue line suggests a dissipation time of about 2 hours later, 1345 UTC. A more robust way to use this might be to compare today's fog depth to yesterday's, if you're in a regime with multiple sequential foggy days, and adjust today's fog burn-off based on the difference in fog depth between yesterday and today. The model data used in IFR probability varies by region. Domains and resolutions are noted on this slide. If you are forecasting outside of North America, you may see probability differences at the model boundaries because GFS and rapid refresh solutions will vary. There are occasionally stray light issues around the equinoxes and brightness temperature difference fields, and that will affect IFR probability fields. Be aware of that. This slide shows the discontinuity in IFR probabilities during the transition from day to night or vice versa. Satellite predictors used during the day differ from those used at night. In general, IFR probability increases during the day because of changes in the statistical predictors used, in part because the satellite is more confident that a cloud is present when it can use visible data. GOES-R cloud thickness products are not computed during twilight conditions, but it is available all night and during most of the day for single-layer water clouds. GOES-R has routine 5-minute data. This is handy when precise information on dissipation time is required. If you need even more precision, request a meso and get 1-minute data. You'll note in this animation the pulsing that's happening at the top of the hour as new rapid refresh model run is incorporated. So every hour, a new rapid refresh model simulation is being used. Forecast hours from 2 to 3 hours are used in IFR probability fields. GOES-R IFR probability is statistically superior to brightness temperature difference fields in predicting IFR conditions. You should already know why that's the case. If high clouds block the view, IFR probability can give a good signal based on the model data. If stratus is elevated, IFR probability will screen out the regions based on model data. Both of these examples will lead to better statistics for GOES-R IFR probability. Brightness temperature difference fields are challenged to provide information about cloud ceilings, as the satellite sees only the top of the cloud. Brightness temperature difference fields cannot give information when high cirrus obstructs the view of low clouds. IFR probability fields in these cases can augment the satellite to give a more complete description of the near-surface saturation. GOES-R cloud thickness fields can be used to predict fog dissipation time. As always, use as many products as possible when you're trying to figure out where the fog sits. I've talked about satellite imagery here, but you can also use surface observations and webcams to great effect. You can click on these links to find more information on the product. These links are also available at the launching page of this module. This concludes the Satellite Foundational course for GOES-R on fog detection. Thank you for listening.